So test preparation claims that 50%, more than 50% of students who take the test prep improve their scores. Instead of advertising a percentage, managers suggest testing whether the mean score improves at all. For each customer, they record the differences. Okay, so right now they say, hey, 50% or more of our students do better after they take our test prep. The manager's saying, well, let's look at things a different way. Let's just say how many points are on average our students improve by. So we're supposed to state the null and alternative hypothesis. So the one I always focus on is the alternative first. And then that's what they're trying to find evidence to support. Instead of advertising the percentage of customers who improve by at least 10 points, they record the difference in score before and after taking the test. So they're wondering if the mean is greater than 0 here. Okay, that's what they're trying to find evidence to support. That's because of this sentence right here. A manager suggests testing whether the mean score improves at all. So if if this difference is greater than 0 is what they're asking for. Because like let's say your score before was a 90. Your score after was 100. 100 minus 90 is a positive 10, right? That means you increased by 10 points. So they're testing to see whether your mean score, and this should really have a subscript position D here to say it's the mean difference, is greater than 0. Okay, it's not greater than 10 or less than 10 or anything like that. We're not comparing it to any other ones. We're just seeing if there's an improvement. And so the null hypothesis would be that the difference between the two is the same. You know, if you take your test prep software, it doesn't change your score. It has no effect because the null hypothesis is the null effect model. The p-value is 0, so it's fairly large. A p-value of 0.5 means it's a 50-50 chance that the test is actually improving the score. A p-value of 0.65 is really large. Okay, significant p-values are usually less than 0.05. So this p-value is fairly large. It's nowhere near 0.05, which is really where we want to be for a small p-value. So this it doesn't provide weak evidence. It definitely doesn't provide strong evidence, but it doesn't provide weak evidence either because it's nowhere near like that arbitrary 0.05 cutoffs. It's little to no evidence. This is saying there's a 65% chance that the test is actually improving your scores, assuming that the 0.65% is the probability that that we get this test statistic, assuming that the null hypothesis is true. So roughly speaking, it's a probability that the null hypothesis is true. So there's a 0.65% chance that this is true, that the difference between your before and after scores is just going to be 0, that there's no effect. Okay, so that's little to no evidence for the alternative. Little to no evidence that it's improving our scores. Choose the correct answer below. The mean difference for the sample was negative. Do we have a sample? Oh, 0.65. Okay, so this is kind of a theory question here because we don't have the actual numbers. And they asked to see, it's a one-sided test. So let's get rid of this. It's unlikely to be Z, but let me draw a picture. I think that'll help us answer that question. I'm actually not sure right off the bat, but I bet we can figure it out. Okay, so 0 means that the test gave us no improvement. A -1 would mean that the test actually, on average, made students drop a point. And a +1 or +10 or whatever number you want to put over here, a positive number means that the test helped us improve our score. So the 0.65 is the p-value. And what that means is that 65% of the area is in the tail that's determined by the alternative hypothesis. Our alternative hypothesis is that the mean is greater than 0. Okay, so this is a right-tailed test, and this is saying there's 0.65 in the right tail. In other words, 65% of this graph needs to be in the right tail. Remember, this is the 50% cutoff. So 50% is in the right tail right there. That means the 65% cutoff needs to be somewhere over here, right? And so that means that this is a negative value. It's actually, on average, the sample had, the mean difference was negative. Could have been within one standard deviation. That's not necessarily true. We don't know what the standard deviation was, but wait, 0.65. I know A is true, so all the other ones have to be false. The mean difference of the sample was positive. That's not true based on our drawing. We can't determine exactly how many standard deviations, or can we? Within one standard deviation. I mean, the p-value, that's the probability that z is greater than some test statistic, we'll call it z sub 0. No, okay, so we can't because we need to know what the sample mean is, because to calculate this probability you need a z-score, and to calculate the z-score you need to know what the actual sample mean was, and you need to know what the standard deviation is. So we can't determine the standard deviations because we don't have the mean, the actual numbers for this test. Maybe if they gave us the mean, maybe that'd be a complicated work backwards from this type of question, but for that reason I explained above, that it has to be negative because I drew that p-value for us.